Now that we've been doing techniques for a while and become hopefully pretty proficient at taking derivatives, we're going to take a minute and maybe a few minutes and talk about some applications. And one of the favorite ones that comes up about this time is called related rates. And it may not be your favorite, but it's kind of, well, it's important because this actually starts taking the techniques that you've acquired and applying them to situations that are fairly, I guess, simplistic in the fact that a lot of the situations are contrived, wouldn't necessarily be something that you would investigate in the, real world after you graduated. Or the typical ones then are a little bit more complicated, but you have to start learning how to do this somewhere. So we're going to start with these related rates. There's sort of a pattern to them. I think it's a little hard to identify sometimes, but basically what happens is they are talking to you about a situation and they describe it to you. And they say, this is a situation. It looks like this. It's set up this way. And they give you this picture of this is how it starts. And then it says, then we start doing this. The process is starting to do something, depends on what the process is. And then it's like you take your camera, maybe it's your camera in your phone, and you just look, oh, that's interesting, and you take a quick snapshot of it while this process is going on, and then you try to analyze it at that time. Now, trying to get all these bits and pieces to fit together, it just takes a little bit of practice. After you've identified how this sort of works, I know this sounded very vague, but when we do a few problems, I think it'll make more sense to you because no two problems act alike. So it's not like I can say you do this, and you're done. I can give you some guidance, and then you just have to practice a lot. And then you start seeing kind of trends like, oh, that might be kind of like this one. All right. So let's start a problem. And this is a fairly common starting spot for a lot of these problems. They talk about a ladder leaning up against a wall. And, you see that every day. That is definitely a real life situation that goes on. You've probably seen ladders for people painting the sides or whatever. But this is talking about a ladder that's sliding down the wall. And I've worked with ladders before, and you don't usually just let them slide down. You run over there and prop it back up and set it up a little bit more. But, we've got to start somewhere. This is it. These are story problems. Okay. Sometimes I think more story than anything, but find a laugh in here where you can. All right, so let's start off with this problem, and let's go over here and do the ladder first. And it says a ladder 20 feet, 4 feet long, is leaning against a vertical wall. The bottom of the ladder is 6 feet away from the wall per OSHA safety recommendations. I actually looked that up. It's a fourth of the working length of the ladder. All right, in case you want to know. The base of the ladder begins to slide away from the wall at a constant rate of 4 feet per second. What is the rate at which the top of the ladder is sliding down the wall when the base of the ladder is 8 feet from the wall? Now, what you have to do is to find some sort of a relationship, an algebraic relationship, maybe it's a trig relationship. You try to find something in math that describes this situation. So oftentimes a picture is worth a lot. Okay, so what you have is you have this wall. And then you have a ladder that's leaning up against it. So let's say it's leaning like this, right? And this part starts sliding away from the wall, sliding along the ground. This is not drawn to scale. And as it draws that part away, the top is going to slide down. Now you look at this and you go, well, now what kinds of information they gave me? They gave me the fact that the ladder is 24 feet long. Okay, so I know eventually this is going to be 24. Might be important to know at some point eventually in the problem. I know that originally the bottom of the ladder was 6 feet away, and then it started to slide. So what it might have done was to start here at 6 feet. My engineering teachers would be dying right now going, you really can't draw it like that. So you could draw what it looks like when it first starts. I had to wait a minute because my computer wouldn't keep up. So it starts off 6 feet here, and it would have been a little taller, so it would have been something like that. And then it starts to slide down. And then it moves over to 8 feet. Now, all of that is interesting, but I don't know that I'm going to necessarily need all of that for my problem. Some people have you do, and some people choose to do, listing all your knowns before you actually start working the problem, and then and what it needs, and then you use those. But I had my favorite math teacher was somebody who would throw in tons of extra information that really didn't pertain to the problem at all. And when I first started with him, I thought every number was important. You should use it somewhere. And he broke me off that pretty quickly. So just because they give you a number doesn't mean you need to use it. So what I learned to do out of self-defense really is I would set the problem up and then see which numbers I actually needed. Okay, so let's talk about this. So what happens is we've got this little situation where you can see this is the ground that's supposed to be right here. Okay, and so can you see how this is looking like a right triangle? Because they said it was vertical, which means this would be vertical grounds horizontal. That's the assumption in the story problem. So what makes it a story problem? Because in a lot of life, it's not parallel. It's not flat ground. Okay. So what we're going to do is say, all right, I don't know. Let's just label this X and let's label this Y. And it starts with a distance of 6 feet and it's going to move out to 8 feet. But I'm going to hold off on that for just a second because the first thing I need to do before I start applying any information that they gave is I need some sort of algebraic relationship between all these pieces and parts because this related rates thing says you have some related information. Okay, different pieces that are related to each other. And we're going to talk about the rate at which they're going to change. So I need to relate all these bits and pieces together. So you sit here and look, what do I know about a triangle? I could find the area of a triangle. I could find the perimeter of a triangle. I can talk about the angles of a triangle. But what I need is something that relates these two legs of the triangle to this longer length, which is the hypotenuse. And you sort of just go through everything you know in your mind and you go, wait, there's a Pythagorean's theorem that relates these two legs to the hypotenuse. And what you would have in a generic sense is this would be 24, this would be x squared x, this would be y. And over here, we may be thinking about, it starts off at 6 and it ends up being 8 over here. But for right now, I just need a generic x and y. So we're going to use this for specific information. Information. All right. And we're going to use this for our general relationship. Okay. So our general relationship is that x squared plus y squared would be equal to, now in this case, it's 24, because that's never going to change, right? The length of the ladder is never going to change. So this could be 24 squared. Okay. Now, this is our relations. This is the part that's related to each other. It's the legs and the hypotenuse. And now we're going to find the rate. And anytime they ask you for a rate, what's the rate of change or what's the speed that something is happening at, unless they say average, well, Usually when in physics there's a difference between velocity and speed, but for right now, let's just say the rate of change is often referred to as speed. So if they're saying something like that, that means to take a time derivative, not the derivative of something with respect to x or to y, but with respect to time. So what I'm going to do is to take the derivative of this x squared, y squared, and 24 squared with respect to time. And since these are not t's, then that means everything is treated as implicit. And if you don't remember how to do implicit, you need to go look, because you can't do these without that. All right. And there's a previous video that talks about implicit. So we're going to talk about how to do this. So you bring the 2 down, you leave the x alone, and then you loop back in and take the derivative with respect to t of x. You bring the 2 down, you leave the y alone, you loop back in and take the derivative of y with respect to t, and the derivative of a constant with respect to anything is 0. All right. Now, you sit here. I'm going to shrink this down just a little bit. And this is what I do. I go, all right, I need to find some portion of these 4 variables. Can you see the 4 variables? So here's one of them. Here's the second. Here's the third. And here's the fourth. So there's 4 variables. And if they want you to solve for one thing, then you have to know 3 of them. Okay, so solving for one variable requires one equation. If you have to solve for 2 variables, you need 2 equations, and 3 variables would be 3. But so I'm going to be looking for this information. So let's see what I've got up here. All right, now the 24 feet, this 24 feet, this basically just set up for right now. All I needed it for was this right here. I think I may need it later, but the 24 feet is the length of the ladder. So if this is my specific information over here as well, I have my 24 feet right here for my specific information. Leaning against the vertical wall, the bottom of the ladder is 6 feet away from the wall. Okay, so I've got kind of my little 6 right here labeled. That's from here to here, 6 feet. And the base of the ladder begins to slide away from the rate at a constant rate of 4 feet per second. Okay, now the base is this part right here with the black. This is the base right here. And this is moving away in this direction. And so that's the change in the x position, right? So that 4 feet per second is dx dt. Okay, so dx dt is equal to 4 feet per second. Now, I also needed to know what x was, and x is the distance away from the wall. And I have 2 possibilities. So I have the base starts off 6 feet away from the wall, and then down here it mentions 8 feet away from the wall. So let's look at the question again, and it says, what is the rate at which the top of the ladder is sliding down the wall when the base is 8 feet from the wall? So they're not asking you about what it's sliding down when it's 6 feet from the wall. It says, what is the rate when it's 8 feet from the wall, right? So the number that we need for this specific information for this little snapshot picture that we took, remember I said you see something happening, oh, it's sliding away from the wall. And instead of rushing over there to stop it, you're going to take a picture and say, wonder how fast that is. All right, so here we go. So the x that I need is that 8 feet because they're asking me about what it is at that time. Okay, now I also need to know what y is. Now, y would be the distance that it's at, when this ladder pulls out to 8 feet, right? So when this ladder pulls out to 8 feet, it wants to know what this y value is here. How far up the wall is it? And do I know that? It doesn't look like I do because they didn't give it to me. Okay, so let's hold on for that just a second. We'll come back to that, all right? And the other piece I need to know, or the question they're asking, is what's the rate it's sliding down the wall? And that would be the change in its position along the wall. So this one is the one they want me to answer. So that one is something I'm supposed to not know. I'm supposed to discover. I'm supposed to solve for it. So that means, and I'm just trying to work you through how you figure this out. So if this is the one I'm supposed to find out, if dy dt is the one I'm supposed to solve for, right? That means that there's no information given that way, right? So that must mean that there's some way for me to find out why. So what you do is you sort of walk through there and say, okay, I know for sure what this is. I know what this is. I know what this is. And then if you get down to one or two that you don't know, find the one that you're supposed to solve for, and the other one, it must be hidden and you just haven't figured out what the number is yet. Okay, so let's go back up here to my specific information. And I know that from here to here is 8 feet. And I know that from here to here is 24 feet. So if I know that at that instant I took that little snapshot, this is 8 feet and the other one's 24 feet, hey, can't I use the Pythagorean theorem to find y squared? Or y, right? Because I'm going to use y squared. So what you would do is you would go, okay, well, x squared, we're going to go back to this, plus y squared is equal to 24 squared. And I know that at this instant in time, x is 8. So 8 squared plus y squared is 24 squared, right? So y turns out to be the square root of 512 after you kind of go through the math, right? And this turns out to be 16 square root of 2. So this y here is 16 square root of 2 feet, right? So what we're going to do is to take this equation right here, let's label it 1. This we only have one equation, right? And we're going to start filling it in. So we have 2. X is 8 feet. Okay, dx dt is 4 feet per second, right? Plus 2. Y we've just discovered is 16 square root of 2 feet. And dy dt, well, that's what I'm supposed to discover. So I don't know what it is. Okay. So when I set this up and solve it, I can just move everybody around, right? And so you would multiply and divide and all this other good stuff, and you would have dy dt is minus 2.828 feet per second. I should make that look a little bit straighter. Sometimes I struggle a little bit when I teach math because the way we do the units in engineering is a little bit different. Okay, so sometimes yeah, it's kind of crazy. So I don't know where you want to round off. Your teacher's going to tell you, and so we're going to do it the engineering way, and they just always round off to 3 in the book that we use. All right, and so you don't have to consider significant digits. If your teacher likes that, you should do that. All right, and the negative just says that it's going in the negative y direction because it's sliding down. So that kind of makes sense. And I think it's reasonable, right? If the base is moving at 4 feet per second, you wouldn't want the top of the ladder to be going at like 16 feet per second or something like that. All right, now let's look at another problem. Now remember what they're doing is it's like you're watching this activity taking place and you're describing the activity and then you take a quick little snapshot of it and ask a little question. And it's so almost seems like which came first, but you try to find some sort of a relationship between the topic that it's talking about where it relates all of the individual pieces of information. So in the previous example, we talked about ladder sliding down the wall, and so I needed something that related the sliding out from the wall and the sliding down the wall, and we decided the Pythagorean theorem would relate those two together. Sometimes it's a little bit more straightforward, so let's look at this one, and it says air is blown into a balloon at the rate of 200 cubic inches per second. What is the rate the radius is increasing when the diameter is 8 inches? So this one isn't necessarily relating one measurement to another one. This is just saying you have a balloon and you're blowing it up. Now, most balloons, you have to kind of remember these are story problems, okay? And story problems are not necessarily 100% real life. There's a little bit of a made-up story. So we're not talking, these long cylindrical balloons where you make little animal figurines out of it or something, or these humongous balloons or these ones that look kind of like a thick pizza or something. We're talking about just a traditional, almost round shape, and they're going to approximate it by saying it's a spherical shape. Now, that's not in there. You just sort of have to assume that. And this is a very common problem. So it's saying, okay, we're talking about a sphere. And this part where it's talking about 200 cubic inches, you go, well, what are they talking about? The sphere. If they're talking about cubic inches, they're talking about a volume. If they're talking about square inches, they're talking about an area. So since they refer to one of the units as cubic inches, they're talking about a volume. So you think, well, what do I know about the volume of a sphere? Well, what you know is there's a formula. And I don't know if your teacher is going to tell you the formula, put it on a formula sheet, or if you're supposed to memorize these basic formulas. You need to check with your teacher and verify whether you're expected to be bringing this information inside your brain, or whether you're allowed to have a formula sheet, or if that's going to be provided. So the formula for what's the volume of a sphere is 4/3 pi r cubed, where r represents the radius. All right. Now the question says, what is the rate the radius is increasing when the diameter is 8 inches? And that implies they want to know how quickly that's happening. That's one of those related rate problems. So if it's how quickly, how fast, how long, anything that's implying a speed in any way, that's saying you're going to take a time derivative. So we're going to take the derivative with respect to time. None of these are t's for time, so this is implicit differentiation. So when you do that, the derivative of v with respect to t is dv dt. And you have your 4/3, and your pi are just coefficients that multiply r cubed. So you bring the 3 down, leave the r alone, drop 1 off the power, loop back in and take the derivative of t derivative of r with respect to t. I think I said it backwards. All right. Now, luckily for us, this is good. This 3 cancels this 3. And so we're going to continue on. And so this is going to be 4 pi r squared dr dt equals dv dt. All right. Now, let's see how much of this information we know. Now, what is it that we're actually being asked for? That might be where you want to start. And you go, right, this is what I'm asked for. So I'm not expecting to see information on that. But that means that somewhere hidden in this problem statement must be a value for r and must be a value for dv dt. Otherwise, there's too many unknowns. So you look and go, all right, what is the rate the radius is increasing when the diameter is 8 inches? Be careful that if the formula has radius, they may give it to you in a diameter, which this is. So if the diameter is 8 inches, the radius is half that, right? So this implies that the radius is 4 inches. You with me so far? And this is dv dt. Because, see, if you look at the units for dv dt, you're expecting a volume measurement. divided by a time measurement. So cubic inches divided by seconds is a volume divided by a time. So we're going to substitute in what we know. And so we have 200 cubic inches per second is 4 pi. R is 4 inches squared times dr dt. So we're solving for dr dt. All right, 4 times, let's look at these parts right here. So 4 squared is 16 times 4 is 64. So what I'm going to be dividing is 200 cubic inches per second divided by 64 pi square inches, right? Because this right here is 64 pi square inches. All right, now we can clean this up just a bit. Remember, there's a difference between exact answers and approximate answers. And if they don't tell you to round it, they're wanting exact answers. So if we had exact answers, what we can do is to reduce this and come up with that number. And then we would have just our pies left over, right? You hanging in there? Now, so when we reduce that, and we would have 200 divided by 64 is 3.125 over pi. And we had, that doesn't even look like a pi, over pi. And we have cubic inches right here divided out square inches. So this turns out to be inches per second, right? Now, this is the exact number. And while that might be good if you're going to feed this into a computer or into another function that you're going to evaluate something else, it doesn't really necessarily mean anything to human beings as far as a number. If you divide that out, it turns out to be 0.995 inches per second, which means, well, it's almost an inch every second. So an approximate answer is normally what humans kind of relate to better, but computations, computers, future functional evaluations using this value, you would need to use an exact one. So I hope you're doing okay so far. Now let's kind of talk about this again, a variation on this theme. Again, we have, this is the same balloon before, and it says, what's the radius when the rate of change of the surface area and the rate of change of the radius are equal? Now, this one had a little clue word right here. You look for clue words. This is the surface area of a sphere. So we're not going to use the volume equation. We're going to use the surface area, and let's just call that S. So we would say S is equal to 4 pi r squared. That's the formula for the surface area of a sphere. So let's take the time derivative to talk about the rates and see what kind of information we need, because frankly, there's not really anything specific here as far as numbers. So the derivative of s with respect to t. Then you have your 4 pi, which are just coefficients. And then you would bring down your 2, leave your r alone, take 1 off the power, and loop back in and take the derivative of r with respect to t. Now, so this turns out to be 8 pi r dr dt ds dt. Now, what they're wanting And see how many well, let's talk. They want to know what is the radius. So what they want to know is this right here. That's the question, which means I need to figure out something about these other unknowns because I don't know what DRDT is exactly. They didn't say it was 2 or 3 or 1.59, and I don't know what DSDT is either. But I need that information to come up with R, because if you only have one equation, you can only solve for one unknown. So I've got too many. All right, so let's look back and read it again. And it says, what's the radius? Okay, that's R. When the rate of change of the surface area and the rate of change of the radius are equal. Now, the rate of change of the surface area is ds dt, and the rate of change of the radius is dr dt, right? Because rate of change is a time derivative. All right, so what they're saying is these two things are equal. So if these two things are equal, I could actually divide them out from both sides, right? Because they're equal. If you same thing as if you have 2x is equal to 2y. Okay, well, if this 2 is equal to this 2, then this x has to be equal to y, right? Because technically what you're doing is dividing both sides by 2. So if this term here is equal to this one, okay, then I can technically divide those both out, or say if those two are equal, then 8 pi r has to be equal to 1. Okay, and then r is equal to 1 over 8 pi. And that's kind of interesting to me because the r turns out to be 1 over 8 pi, which has nothing to do with the size of our balloon, right? That doesn't have anything to do with it. And I just find that fascinating. So r is 1 over 8 pi inches if what we're dealing with is a balloon in terms of inches. That would be exact. And if we want to approximate it to it'd be 0.0397 inches. Or if they want you to round it off to like the nearest hundredth, it could be 0.04 inches. So you would need to pick, whatever ones you want to use. All right, hope that helped a little bit. Let's do this car leaving the parking lot problem. This is sort of a different variation on, it's actually kind of a variation of the ladder problem, I think you'll see. So let's try this. And let's start with this problem. And it says car A leaves the parking lot at 6 p.m. traveling west at 45 miles per hour. Car B leaves the parking lot at 7 p.m. traveling north at 60 miles per hour. At what rate are they separating at 10 p.m. if they have not changed course or speed? That's a good question. So we have a parking lot. Again, it helps sometimes if you draw a picture to try to figure out what you're doing. And so car A is going to leave the parking lot at 6 p.m. traveling west. So let's say this is west. So they're going to travel west at 45 miles per hour, right? And this is car A. Excuse me. Car B leaves the parking lot traveling north. Let's say this is north. And they're traveling 60 miles per hour. And this is car B. And I'll worry about the time in just a second. But I just sort of want to get my head wrapped around what's physically going on. So I've got one car going west, one car going north. And what they're actually trying to figure out is how quickly are they separating between there and there. Okay? Now, let's talk about, so I kind of have this, it looks kind of like the Pythagorean theorem again, right? Because this is related to the two legs, and the separation between the two, this is talking about the sides. It isn't talking about the angles that they're making. It isn't talking about the total distance or anything. It's just talking about the relationship between the two known distances and directions as opposed to the distance between the two of them. All right. So I think I'm going to go for the Pythagorean theorem. And so in order to do that, I think I kind of need to talk about a couple of things. First off, I'm going to set it up as um, first an unknown. So this would be something like x, and this is y, and this is r. And so I'm going to use this Pythagorean theorem for x squared plus y squared is equal to r squared. Okay? But when I take the time derivative, I want to show you what kind of information you're going to need. You'd bring the 2 down, leave the x alone, take the derivative of x with respect to time. Bring the 2 down, leave the y alone, take the derivative of y with respect to time. And this r squared is not a constant like we did in the ladder problem because r is growing as they separate from each other. So you bring the 2 down, leave the r alone, take 1 off the power, dr dt. Okay. Now the 2's, you can cancel those out. And I would probably suggest that you do that, but I'm going to leave these in so that we're not distracted by this at the moment. So what this is saying is this image of the activity of the cars driving off and separating each other. And then I'm going to take a snapshot at 10 p.m. All right. So they've been doing this activity for a while. They've traveled some distance away from each other. And I now kind of freeze frame it or take a snapshot and I'm going to try to analyze it. So what I'm going to need to know is I need to know the x and y distance that they get to, right? I need to know how far they've traveled in the x direction and how far they've traveled in the y direction. I also need to know how quickly they're moving in the x direction, which I actually know that's 45 miles an hour, and how quickly they're moving in the y direction, that's 60 miles an hour, so I know those, right? And then drdt is what I'm being asked to find, right? How quickly they're separating. And I would need to know R. So I'm kind of not being supplied with X, Y, and R's measurements. But do we have enough information to find it? So let's look again. So let's look at another variation of my triangle. Okay, so car A. Let's talk about car A. Car A, looks like Kira. Car A, all right, leaves the parking lot at 6 p.m., travels at 45 miles an hour, and we look at to see where it is at 10 p.m. So car A has been traveling for 4 hours when I take that snapshot, right? So in 4 hours, how far would they have gone? Well, 4, and A is traveling at 45 miles per hour. So for 4 hours at that rate, okay, then we would have 180 miles, right? Okay, so this distance is 180 miles. Now, car B is, let's see, they start traveling at 7 p.m. They don't leave at the same time. And we take this snapshot at 10 p.m. So it's traveling for 3 hours. So 3 hours at 60 miles an hour, because they're going a little faster, is also 180 miles. So this is 180. Now, using Pythagorean's theorem, I can then find r. So it turns out to be the square root of 64,800, right? Because it's 180 squared plus 108. Let's do this. So 180 squared plus 180 squared is equal to r squared, right? So r is equal to the square root of 64,800. And so when you clean this up, it turns out to be 180 square root of 2 miles. So this is 180 square root of 2. Okay, so this is x, this is y, and this is r. So it took me kind of 3 variations of the triangle to get there. So you have to be willing to play with these problems. Now with the balloon, we didn't really have to play very much, right? It was just a simple, I'm talking about the volume, here's a formula. Okay, plug in the numbers after you take the derivative and we're good. This one has to be a relationship we're building. It's just a little bit more complex. So it may take you a few more minutes to kind of work your way through this, but don't let it discourage you and don't give up on it. I would strongly suggest that for me and for my students that you come up with what formula do you think you want to use, and then you take the time derivative of it, and then you go back and go, the rest of this information has to be here somehow, some way. I have to be able to arrive at it once I know what it is that I'm looking for. And remember, what you're looking for is this part right here. The question determines kind of where else you're heading. So go and find, get your formula, get it set up. This sort of gives you a guideline of what to do next, and then look for your knowns and unknowns. And I'll be honest with you, if your teacher wants you to start off by doing the unknowns and knowns, then just leave a big old blank space up here, okay? And come down here and do this, and then loop back up and put in the blank space all the things that you need and that you found. So you can do this, all right? And if you like putting the knowns and unknowns at the beginning, there's wonderful concepts and ideas about that. But not everybody can see all these things right off the bat, but they can see them once they have determined what they need. Okay, back to the problem. Sorry. Here we go. So I'm going to fill it in. So I have my 2. Okay, my x is 180 miles. Okay. Then my dx dt is how quickly I'm moving in the x direction, and that is 45 miles per hour. Okay, plus 2. And again, you can divide by the 2's and be done with it. And y is 180 miles. And dy dt is how quickly we're driving off in that direction. And so this is 60 miles per hour equals 2, right? And r is at 180 square root of 2. dr dt, right? So then you have to clean up the left and clean up the right and do a whole bunch of multiplying and adding. And so I've written it down and cleaned it up just a little bit. So it's 37,800. And look, right here you've got miles times miles, which is miles squared over hours, right? Because I'm in this side, I've added these two together, equals 360 square root of 2 miles times dr dt. So dr dt is equal to 37,800 miles squared per hour divided by 360 square root of 2 miles. So see how the mile on the bottom dimension is going to cancel out the one on the top? So that's good. It's miles per hour. I kind of like that. Because this is how quickly. It didn't say how far apart are they. It said how quickly. So dr dt. Now there's all sorts of variations of what you could say here. You could say it's 105 over the square root of 2 miles per hour. If your teacher wants you to clean up any square roots in the bottom of the fraction, it would be 105 square root of 2 over 2 miles per hour. In engineering, we don't ever put S's on here for miles, and so I'm afraid that's a notation I'm teaching you. And then you could also approximate it, which kind of helps us to see what's going on. And when you divide this out, it's 74.2 miles per hour. You doing okay? Okay, now that's going to be the first, this is going to be the end of the first related rates video. I kind of wanted you to take a break before you started the second one, because this, you really need to kind of think about this, let your brain see it, let your brain kind of muddle over it, take a break for a second, come back and go, I think I've got it. Okay, and then look at the next video. So I'm going to force that a bit by stopping this video, and you can start the next one as as soon as you want to, but I'm hoping that you'll take just a little bit of break. Could be just a few minutes, could be go get lunch, or whatever, but then come back and watch the second one. All right, see you in the part 2.